that is gamma is left orderable, and every order and has no pre-subsemi group, then every order is valid. But of course, the converse is not true. The converse is not true. Is that there is a group, list of Sarani's group, where there are subsemi groups. And group like the bounce solitary group. To conjugate B by A not to B to the square. Okay. And on this group, there are only finitely many. Therefore, since there are only finitely many left orders, every order on this group is convariant. This is what we saw yesterday. So if you have a finite orbit in the space of left orders, the orders in this orbit are convariant orders. Okay, but the question is a natural one. So the question is whether there exists a group gamma with many orders such that every order. Sorry, I'm not asking the right way. So, yeah, every order is convariant, and it has this subsemi. Okay, that should exist. I mean, perhaps this is not the right question. So the right question to ask is whether there is a characterization of groups for which every order is convariant. So I'm going to write this. Just for an example is, I'm just realizing that that should be simple, but the question is final characterization of groups, left orderable groups, all of these orders are convariant. It's something that I don't know whether it should be interesting, but actually there is a theorem. I don't remember exactly who proved this. I think it was Recula, but I am not totally sure. Maybe not. In any case, this classical theorem is in the book. Botomura is that if gamma is left orderable, and every order on gamma, every left order on gamma is a bi-order, then actually gamma is abelian. This is the kind of thing that we would like to know whether there is some analog of groups having only convariant orders. And of course, there is this example, so I don't know, maybe all groups like these are solvable.
Thank you. Yes. Oh. I don't know if this works, Mal. One candidate could facilitate.
Yes. Okay. So if I go into the basilica, yes, the candidate. So okay. Michele says that there is a natural candidate. Okay. Yeah. You take me. Maybe you can tell us about in the problem session. Yeah, but this is a natural candidate. Because actually there are many groups, so there are very interesting groups without subsemi groups that are left orderable and that are not impotent. Groups of exponential growth that are left orderable. And these groups, this proposition applies. But the basilica group has subsemi groups, free subsemi groups, and it's very close to those groups. So this is very good idea. So very good. We have a high answer for this. Okay. This is more than question. This is like can be stated as a question. So one can consider it can be done in the space of left orders, in the space of bi orders. In this case, in the space of convariant orders, it is solved by the theorem of Ribas that says that the space of Canadian orders here is finite, but it is a Cantor set. There is no intermediate possible. But here the question is, the program is to study the Cantor-Bendixson rank of an order. Okay, what is the Cantor-Bendixson rank? So it depends on the convention, but the rank, you take a metric space, the rank of an isolated point is equal to 0. And if there is a point which is non-isolated, like this point, but which is the limit of points which are isolated, then the rank is equal to 1, and so on. So the rank of a point is equal to the how to define this.
You remove points of rank. You want isolated points.
If you remove point of rank 0
of less rank, smaller rank, then you want to be isolated.
Okay, so let me define by induction. Xn will be the points of rank n, and X as rank n plus 1 if it is isolated, and X belongs to X minus Xn, then if it is isolated in this cell. Is it okay? So a point of rank 2 would be a point for which there is a sequence of points converging to it, and for each point of this sequence there is another sequence of points converging to each of those, and these points are so far the only thing that we slightly understand is the fact that in the space of left orders and also in the space of by orders, in the space of left orders, for instance, in the space of orders of the Bray group is like a Cantor set. Okay, this is a Cantor set, and there are many, and there are some isolated points. Okay, for instance, here one Cantor set is the closure of the orbit of the de Horno order. Okay, this is a Cantor set in the space of orders, left orders of B3. And there is an isolated point, the order by Dubrovin and Dubrovin. So remember that the order of Dubrovin and Dubrovin is easier to describe. It comes from the fact that B3 has this decomposition. And the order of Dubrovin and Dubrovin is the one for which this is the positive cos. Okay, and this order is harder to introduce because the positive cone here cannot be finitely generated as a semigroup, otherwise it would be isolated. So this order is isolated, but actually the orbit of this order is very particular. There is a sequence of conjugates that all isolated points that converge to the Horn order. Okay? There exists a sequence of elements in B3 such that if you apply these elements to the Dubrovin and Dubrovin order, what you get in the limit is the Horn order. Okay, so you convert somehow to this Cantor set. And but I don't know whether there are points here which are or Cantor-Bendixson rank equal to 2.
We know that every point in the Cantor set is accumulated by something like this, or just that they accumulate to the one?
No, because if you take this order, since this order is a recurrence point of itself, then its orbit, the closure of its orbit is a Cantor set. So if you converge to this one, actually you okay, so there is a nice dynamics here. So this is just a Cantor set. Maybe there are many Cantor sets inside. I think there are. Maybe not for B3, but if you go to B4 or B5, you get many other orders. So this is the question: whether in the space B3, in the space of left orders of B3, there is an order whose Bendixson rank is equal to.
Is this rank always defined, or?
No, it can be. No, for instance, you take a Cantor set, or you define as being. No.
No, because it's an ordinal.
Yeah, it's an ordinal.
That's like the ordinal.
You're right. You're right. But here we're interested. What happens outside a potential Cantor? Otherwise, you have always many ways to accumulate the point. Okay. Maybe the space of left order would be three is very simple. It's just this behavior and nothing else. But I'm not completely convinced. I mean, no. That's not true because B3 is locally indicable. It has a Conrad order. It's some Conrad order somewhere. Something interesting to understand. Okay. For B5 is different. For B5 is not locally indicable. There is no Conradian orders on B5, so the relation is totally different. B4 is still locally indicable. So there are Conradian orders. Okay, but this is in general. This was just one example. Actually, in general, I don't know how to produce orderable groups with left orders with a prescribed Cantor-Bendixson.
Did you say that there is a rank 1 point here?
Rank 1 point. No. Isolated is rank 0. So I don't know whether there is a rank 1.
Okay, you don't know.
Maybe there is. I mean, so I try to illustrate the question for this group, but in general, the question makes sense for any group. So maybe here. But the point is that since we know that there are many isolated left orders of many groups, to understand up to which extent they are isolated, somehow equivalent to study the Cantor-Bendixson group.
We don't know any example of rank 1 within any group.
I have no example. Yeah. Do you know an example? Rank 1.
Well, this is exactly the challenge.
Yeah. Because in order to prove that something is rank 1, you will really need to prove something about the whole space of orders. And you can ask the same in the space of bi-orders. The space of bi-order is different because there might be infinitely many, but countably many bi-orders for certain groups. So,
If I remember correctly, all examples of isolated orders that we know have the property that the positive cone is finitely generated as a semigroup, right?
No. I think there is an example by Ito.
Okay.
In one of his papers where he in some way. Okay, so I will come back to that in a moment when I will say a few words about the Conradian solve. I mean, you change the Conradian solve by this bounds like solitary twisted group, you can create something like this. Yeah. I think I am not totally sure, but yeah, that's a good point. So let me state this properly. Okay, so this is the remark. This remark was obtained by Linel. Let's say that there was a kind of remark, but it appears very cleverly in a paper by Linel. Is that if you have an order such that the positive cone of the order is finitely generated, it's a semi-group, then this order is isolated. And the argument is the one that I gave yesterday. Is if you have another order for which all these elements are positive, then the order is the same. And the question is whether the converse is true, and I think the converse is not true. I think that there are examples in the literature, but up to some, it is morally true. I mean, in some sense, but okay. And this is interesting because this is an example of application. And this is why I became interested on this, because the Dehornois order on the brain group is hard to understand. From topology, it's hard to understand, hard to define. But the fact that the that the fact that the disorder is non-isolated in the space of left orders has this implication that the positive cone in the Cournot order is not finitely generated. So there are no finite family of elements in the Bray group, such that the positive elements of the Cournot order are exactly those that belong to the sum. Okay, and what is nice is that in order to prove this, we use dynamics. So we prove that this is non-isolating by proving that it is an accumulation point of its orbit under the action of and well, this is what I prove, and actually a paper with Beast proves more than that. There are generalization of the Cournot order coming from geometry, the Nielsen-Thorson orders, and actually Nielsen-Thorson orders are not integrated. And in many cases, they are actually accumulation points of their order. Okay. Now for biorders, let me say a few words about biorders. This is something that I don't understand pretty much. Actually, I think that somehow collect things that are not in the literature because it is not easy to follow. There is a similar criterion here. If you have a biorder, so in a biorder, the positive cone is not only a semigroup, it is a normal semigroup. And you can ask whether the positive cone is finitely generated as a normal semigroup. If it is, then this biorder will be an isolated point of the space of biorders. Okay. And but this is not an only if and only if, because there is a nice example where you can describe all the biorders, and this is Thompson's group. If you take Thompson's group F, it's a very natural biorder on the Thompson. So when you take an element in the Thompson group, so actually this works for any group of a fine transformation of the real line of the interval. This was a fine transformation of the interval. So you take an element, and the element has a graph. Maybe it equals to the identity at the very beginning, then it becomes different from the identity. So this is a typical element in F. Okay, and you look at this point. So to the left of this point, this is directed. This point could be the origin. Okay, and you declare that this element is positive. To the right of this point, the graph is above the diagonal. Or if the derivative of F from the right of this point is larger than 1. And this is a total biorder on Thompson's group. A total biorder. Really very nice, because again, this is what I say in my second talk. So if you take this biorder and you take the dynamical realization of this biorder, you get a new action of Thompson's group, which is totally different from this action. A new action where the graph of the element do not cross the diagonal. Okay, this is a biorder. Actually, you can do the same. You can take the reverse orders of this, or you can do the same on the right. Okay, instead of taking this point, you take the corresponding point on the right, and there are four biorders of Thompson that way. Okay, and actually there is a theorem by the lab that says that on F prime, well, it is not proven for F, it is proven for general group of piecewise affine transformations, but it applies to F. These are the only. This is a very nice and totally elementary. So just knowing that F is, you need to know that F is. Now I think that for this you just need to know that a biorder is in general body. It is invariant under conjugacy and it is contrarian, so it produces many homomorphisms into R. Okay. There are only four biorders on the commutator subgroup. But this is not true on F, because for F, Well, if you go into there is an exact sequence. So if you take derivatives on the left and on the right, you get homomorphism into Z2. Okay. Take the logarithm base 2 of the derivative up. And it turns out that the kernel of this is the commutative subgroup for F. So this is particular for F. So you know, for group of ways of this is not true, but this is true for F. So when you have this, and the point is that when you have this, you can build a kind of a new order on F, starting from any order on this group, and these 4 orders on F prime. You can put them together, and what you get is invariant under conjugacy. Okay, so you get many biorders, and here is a Cantor set of orders. So this way you get a Cantor set of orders on the tensor biorders of tensors. You get 4 copies of the Cantor set. So there are 4 Cantor sets. This way, so this is like a Cantor set. Okay, and there are still these 4 biorders, and these 4 biorders are isolated ones. Okay, and actually this is the whole space of biorders of some two, except for that there are 4 biorders, and there are still 4 biorders here that I will not describe because are somehow tricky, but there are 8 isolated points in the space of biorders of these 4 ones, and these are kind of modification of this. Somehow tricky. Okay, so this is a total description. This is a paper that we wrote with Rivas. And this is the space of biorders of Thompson. Okay? And again, the proof is totally elementary. It just uses the fact that the convergent homomorphism and the fact that the kernel of this homomorphism is equal to the commutator. But the point is that here you get spaces where there are isolated points, there are Cantor sets. And the positive cone of this is not finitely generated as a normal subset. But again, this is rank 0. Okay. You would like to have something of rank 1, rank 2, and so on. There are many. So I don't know if I will have time to answer it. So another question. So I think that I already asked this question, but I would like to insist on this. What is the Hausdorff dimension of the space of left orders of the free group? What is the Hausdorff dimension of the space of biorders of the free group? And even the convergent. Just proving that it is positive. I think, so I'm pretty convinced it should be positive. And I have no proof of that. Okay. So I'm not sure that it's finite. If you go into the complete description of the orders in C2, one can easily show that this is equal to 0. Okay? This is a very small Cantor set. But this Cantor set seems to be very large in the sense that it seems to be easy to order the tree. Okay, and actually there is a very nice work by Smith, which was completed by Smith and Alan Gray, that gives an algorithm to order to put left orders on the tree. Yeah.
You know something about the Hausdorff dimension of the space of subgroups for a group, the Chabot space. That's the same question for subgroups.
Yeah, no, I don't. Yeah, sure. Same question makes sense. Yeah, of course. Okay, and well, this is like a counting argument. It should be, if you take the ball of radius n, in how many ways you can order the elements in the ball of radius n compared to n. so that there is no internal contradiction. And this is exactly what is in the paper of Clay and Smith. If you are able somehow to put an order on the balls, then this order should extend to an order on the free group in a certain sense with some hypothesis. But the point is that this is really an algorithm. So you can take a computer and try to make some computations, and in that way you can get estimates on the Hausdorff direction and so on. And it seems really very hard, but it is very, very interesting. I don't know if it is finite. It is a nice number. And maybe this is only realized for the free group because any other group has some relation that imposes, I don't know, maybe there is a spectral gap on the Hausdorff dimensions. And I have no idea what's happening. But it is very hard to do the computation. In order to compute this, you really need to understand the whole space of. Well, the other question is about, again, I will consider the space of left orders, but I will consider the question with respect to the action of gamma. This is really hard to understand. And so how bad can be? Okay, this space or the action. For instance, this is a concrete question. So can the action of gamma on the space of left orders be continuous and big gamma? Of course, if gamma is abelian, for instance, C2, the action is trivial. Because every order is a bi-order, so there's no. I'm thinking about something which is at least non-abelian, and with a Cantor set of orders, can be continuous. Okay, so as we show in the space of orders of the Bray group, there is this contraction of the this behavior of that the Cournot order is somehow an attracting order for the dynamics.
And you said this action can have actual.
This action can have, yeah, this is what I showed yesterday. So for the case of the free group, there is a dense orbit.
That's
yeah. What is not known is whether it can be minimal. This is a very, very
is that common?
Common?
It's a dense orbit phenomenon.
So I think the only example that we have of a dense orbit is for the free group. Only for the free group we have okay, so let me state it again. Question can the action of gamma on the space of left orders of gamma. What is really difficult here is to connect the order with its reverse. If the action is minimal, if you have an orbit which is dense, it has to accumulate its reverse order. There are conjugates of the positive elements that make them negative simultaneously. So this happens for one order in the free group, but here we are asking for this behavior for every order. So there are spaces of orders where we know that the full space is divided into two copies, and here the action is minimal, and here the action is minimal. So that's not true. Okay. We are that should be true, but it is not written anywhere. But anyway, it is not that hard to separate the space of orders into two pieces where the dynamics is completely. In general, here we have the reverse orders of it, and it is difficult to connect them. This is one of the key things of this question. And anyway, I think these things should exist. Okay, so today we have to the work of many people, Loga, Hai, Michele, Nicola Mattevon, and etc. We have many techniques to build new examples of left orderable groups. So I think this kind of thing should exist. So I will come back to it. Okay, so let me just finish with a very short discussion on the Conradian property. Okay, and the point is that the characterization that I gave this characterization of the on the residual leaves. So remember the following are equivalent for Aleph order. For every positive element, for every there exists some n such that f g to the n is larger than g, and the other condition is that there are no elements h1, h2, fg such that h1 is smaller than f, h1, g, f, h2, gh1, gh2. Okay. The two conditions are equivalent, and actually they are seemingly not unrelated, but actually the relation comes from the terminology and foliations. So let me remind you that Conrad's proves that if you have a Conrad order, if this is a Conradian left order, then the jump of every element has an Archimedean order, so it embeds into R. But now the point is that when you have a Conrad order, say that the group is finitely generated. When you have an order, you can look at the dynamical realization. This is an action on the real line. And people working on foliations and working on actions on the real line had studied the situation whether there is an invariant radon measure on the real line. Okay? And there is a work of Planck in particular, which says that actually, if and Solodov, instead of looking group elements, you look at an action on the real line. So you have a group acting on the real line. And if gamma has no resilient pair, which is a resilient pair here, is a couple of points on the real line. So let me denote now by A and B, and a couple of elements such that you see this dynamics. So A is smaller than F, A is smaller than F of B, G of A, G of B, B. If there is no such a resilient pair, then the action and gamma is finitely generated. This is important here, it's really important. Then gamma preserves a radon measure, which is a measure which is infinite in general, and so I will assume that there is no global fixed point. It is infinite, but it has no. It gives a finite measure to compass substance. And when you have an invariant radon measure, you can look at the translation number. So for every f, you can look at the measure of an interval of the form x naught f of x. So if f of x naught is smaller than x naught, then you take this number with the positive sign. And this is what is called the translation. This doesn't depend on x naught because of the invariance of mu. And this is a group homomorphism. So in this setting, there is also a group homomorphism into R. That's given by mu. Okay, and this was already known in the 70s. So actually, we had in the Conrad side, we had this conclusion of a homomorphism into R because of the Archimedean property, and here because of the existence of an invariant radon measure. So it was natural to expect that actually these two conditions were the same. Actually, they are. This is where this idea comes from. Okay. But what is interesting is that now you can define the notion of Conradian not only for an order but for an action. So in general, if you take an action of gamma on a totally ordered space, you can say that it is Conradian. There is no points in omega and elements in gamma such that this situation arises. Okay. Okay. And the point is that if you have a Conradian action, then you still have a group homomorphism into R. Okay, this is a proposition. if gamma is finitely generated, this is important always. But otherwise, it's very difficult. In general, it is not true that you can put your hands on a homomorphism, but if gamma is finitely generated and has a Conradian order, a Conradian action, then these Conradian actions create some group homomorphism into R. And you can adapt either the Conrad's approach or this approach. Okay. But the important thing is that there is a natural, totally ordered space where the group acts. So if gamma, again, is finitely generated as a group, you can consider the maximal proper convex subgroup. Let me denote it by gamma naught. So this subgroup may be trivial, but okay, but there is some maximal convex. And this is because the group is finitely generated. You take the largest of the generators, and you take all the convex subgroups that do not contain this generator. You take their union, this is the maximal convex. And now this space, this is not necessarily normal, but this is a totally ordered space. The space of sets. And gamma acts on this space. And what is the idea? The idea is that when you have a group action, maybe the group action is very complicated because there are many things that are happening, but they happen at different levels. And here we are concentrated on the first level of the action, just the first level. And again, this idea comes from Federation theory. Actually, Federation theory is a theory which is called the theory of levels. Okay? And this is exactly doing it. Take the action, and you really don't want to concentrate on the whole of the action, just what happens on the first level. Maybe on the first level it's like a translation action, maybe not. Okay? But you don't want to pass to what happens in deeper sides of the action. Okay, and for instance, you can take any group with a very, very complicated action, and you add some generator, C, and you make this generator commute with the rest of the group, and you add this generator act as a translation in the real. In that case, you are somehow killing the complicated part of the action because in the first level you are putting an action by translation. Okay, and this is the kind of thing that we would like to do. Okay, and well, there is a natural distinction when this action is Conradian and non-Conradian. This action is Conradian, then this gives you a homomorphism into R because of that generalization. Okay, in that case, gamma has a homomorphism, a non-trivial homomorphism onto R, which is detected again only by the first level of it. And in this case, the action is non-Conradian, so there is contraction somewhere. Okay, and now you have two cases. The case where there is only local contraction, which means that, yeah, you are contracting some intervals, but maybe outside the situation, and there is global contraction. So let me explain here what happened. Let me explain why these two situations are different. So global contraction for me is like the action of the affine group. So you take very, very, very large intervals, you can contract them into very, very small. But in general, even when there is contraction, this is not possible because you can start with any group acting on the circle, and you take the leaf to the real line. This is another group that acts on the line. But this action on the line commutes with the translations. So contraction can be only local. You contract an interval, you have to repeat the contraction everywhere. So you cannot contract a very large interval into a very small. Okay, this is the. And the point is that one can show that when there is only local but not global contraction, the action comes from an action on the circle. There is a homomorphism of the real line that commutes with the action. So comes from an action on the circle. And this is a genuine action on the real line. Okay, maybe, okay, so Action on the circle, okay, this is not very precise, but what I am saying here is that the action commutes with a homomorphism of the real line. It has no fixed point, okay? So you can get an action on the circle as a quotient, but maybe you are there is some kernel for this action, but it doesn't. Okay, so this is what we call type 1, type 2, type 3. And this was inspired by the question of linearity. So remember, we proved the theorem of Morris. It says that if gamma is finitely generated amenable, when it is locally indicable, actually the conclusion is that there exists a gamma homomorphism into R which is non-trivial. This is equivalent to saying that it is locally indicable because it applies to every subgroup. The subgroups are of a minimal group. And the question by linear is whether this is still true for gamma without 3 subsemigroups. Without three subgroups.
Sorry to disrupt. So for the definition of current action, so do you want the action to be faithful or something like that? Or otherwise the action can be trivial, isn't it?
Yeah, you're right. You're right. I need to impose some condition. Oh, yeah. I need that in order to this right. I need that the action is cofinite. So for every point there is a group element that moves. In a couple of points there is an element that moves to the right. Okay.
Yeah, but for example, you can take gamma to be a Z times a cyclic group, then you just forget the cyclic group. It's not methodological at all.
Yeah, maybe. Yeah, you're right. You're right. Maybe the action is not faithful. Maybe the group is different. I think it works in general. Yeah. Okay, so this is the question of Hinel, and it is hard to say whether it should be true or not in this. There's some evidence in the positive direction, and some others in the negative direction. So it's really hard to guess what should be the answer. Okay, and so on the optimistic side, we have we have this decomposition of orders type 1, type 2, type 3, and in the case of type 1 order, we have a homomorphism into R. Okay, so this case is good. On the case of type 2 orders, we have an action on the circle, which is obtained as a quotient of this homomorphism. And for action on the circle, there is this weak Tits alternative, the Margulis alternative. So for an action on the circle, either there is a free subgroup inside the group, or there exists an invariant probability measure. And if there is an invariant probability measure for the action on the circle, then you leave it, because this was an action obtained by quotient. So you leave it to the real line and you get a Radon measure which is invariant for the action on the line. And then you get a homomorphism into R by looking at the translation number. Okay. So again, you use translation number and you get a homomorphism into R, which is not clear. So the difficult case are type 3 orders. And well, I want to finish with this because this was a question that I asked in the Mathematical Congress of the Americas 5 years ago, I think, here, one of these rooms. And now we have the answer. So the point is that there are groups for which all the orders are of this type. Very, very complicated. All left orders are. For instance, if you take an affine group, take the boundary solitary group. So most of the orders are of type 2. There is this contraction, actually, are of type 3. There is this global contraction, but there are 4 by orders which are of type 1. The theorem essentially by Loda and okay, is that there exist groups, many groups actually, which are left orderable and finitely generated, such that all left orders are of type. So if there is a candidate to a context example to the inner question, it should be a group like this, a group for which all the orders are of type. Yes.
So you underline that these groups are rather complicated, but you have sufficient conditions for a group to admit a left orderable group to have type 1 or 2. For instance, if you're a 3-manifold group.
Yes. That's, yeah. I have no idea because these are really complicated. Actually, these groups, in the examples, these groups are, well, these are somehow modification of the group of Hyde and Loda. These are simple groups. It's a very, very particular property. Actually, so there is a big theorem by Hyde and Loda, which is not obvious at all that they exist, and there is an alternative proof that I like very much by Nicola Mattebon and Michele Giestino that says that actually there exists finitely generated left orderable simple groups, which was an open question for many, many years, okay? And it turns out that the examples here are simple. And actually there is an extension of this by Loda and someone else, I don't remember who, to get construction of groups like this, which are actually finitely present. Okay, very good question. So this is really in the framework of this kind of groups. The example I did. Okay. Actually, I should say so. I asked the question to Loda, and immediately he came out with an idea how to modify their groups in order to get something for which all the orders are of. But again, if the answer to Linus' question is negative, then the group should be like this, a group for which all the orders are of type. Yes. Yeah, there was a question. Yes.
Yeah, sorry, I missed what you said about the distinction between the first theorem and the second one.
No. This was already a very big set. Okay, this was before this.
I see.
One of the examples of for one of the examples, we can prove that actually all the orders are. Okay? But because it may happen that for type 2 orders that factor through an action of the circle, it may happen that the group is still simple. We have to kill this possibility in order to get something for which all the orders are of type. Essentially, the work to be done. Okay, so I will stop here. Thank you.
Questions?
Thank you, Andre.
Like how you want to know me.
Any questions?
So you didn't say it, but I think they contain free subgroups, no? So they don't answer the question.
They contain free subgroups. Yeah. Okay.
Yeah. Any question? Yeah, let's thank the speaker again. See you back here in about 30 minutes.